Welcome to this explainer. I want you to picture a world-class gymnast competing at the Olympics. The difference between taking home a silver medal and winning the gold isn't about whether they can physically perform a backflip. They all can. It is about perfect form. It's the height of the jump, the extension, and absolutely crucially, sticking the landing without a single tiny wobble. Well, the exact same principle applies to your Cambridge mathematics exams. Today we are focusing heavily on additional mathematics, specifically syllabus 0606, though I want to be clear that these principles stretch beautifully across 0580, 4024, 4037, and 4040 as well. We're going to tackle one of the most notoriously tricky topics on the paper, trigonometric modulus functions. Listen, the difference between a B grade and an A star right here comes down entirely to perfect form and execution. Every single sentence you write, every line of working out, must be a graceful landing. Let's get started.
Okay, let's dive right into this. What really separates a B grade from an A star? It's not just about knowing the basic standard shapes of sine, cosine, and tangent graphs. You see, a B grade student relies heavily on rote memorization. They memorize a shape, they walk into the exam hall, they try to forcefully stamp that shape onto the exam paper regardless of the specific question, and they just kind of hope for the best. But an A-star student, they operate completely differently. They master complex functions without relying on memory alone. They decode the specific constraints of the question in front of them. They understand the command words being used. And most importantly, they explicitly show their analytical process to the examiner.
So here is our roadmap for today's masterclass. 1. The challenge. 2. Core concepts. 3. The transformation arc. 4. An interactive workshop. And 5. Final examiner warnings. Let's jump in.
Section 1. The challenge.
Alex versus Sam.
To really understand this classic B-grade trap we're talking about, let's look at two totally contrasting approaches from our fictional students, Alex and Sam. Now, Alex's approach is to essentially word vomit onto the page. Alex writes down every single thing he knows about trigonometric graphs. He completely overloads the examiner with raw mathematical facts. He'll list out the period, the amplitude, the axis intercepts, but he provides absolutely zero critical analysis linking those facts to the specific question that was actually asked. Sam, on the other hand, is an absolute speed demon. Sam sees a modulus function, panics a little, and rushes the execution. Because they're rushing, Sam completely misses the specific context, ignores the domain given in the question, and totally whiffs on the required format. If an examiner were grading these two papers, you would see red pen marks everywhere for failing to actually answer the specific scenario presented.
Section 2. Core concepts. The precise mathematical boundaries. The entire architecture of Cambridge mathematics rests on precise definitions and causal relationships. You cannot just eyeball a graph. You have to logically prove its boundaries. The syllabus explicitly limits trigonometric modulus functions to the forms y equals the absolute value of a sine bx plus c, a cosine bx plus c, and a tangent bx plus c. But I want you to look really closely at the constraints in those brackets. The parameter a, which dictates your amplitude, will be a positive integer. The parameter b, which alters your period or frequency, will be a simple fraction or an integer. And c, your vertical shift, is an integer. You absolutely must identify these parameters correctly before your pen even touches the paper to sketch or solve. And let's not forget the modulus part, those absolute value lines. That means whatever negative y values you generate must reflect cleanly across the x-axis. Sticking the landing here means making sure those reflected points are drawn as sharp cusps, not lazy, smooth curves.
Before we continue, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 3. The transformation arc. The method marks strategy.
Now notice how the assessment objectives actually break down on this table. Top students make sure they hit every single cognitive domain in their answers. For knowledge, you have to understand definitions, like correctly identifying those A, B, and C parameters we just covered. For application, you need professional execution. This means using appropriate formal mathematical terminology, like explicitly stating the amplitude or the periodicity. And finally, for analysis, you need evaluative thinking. This is where you justify your graphical sketches or your algebraic solutions with clear sequential working out. I can't stress this enough. In Cambridge exams, examiners award marks for the analytical process, not just for having a final magical answer appear at the bottom of the page. You are building a rock-solid case for the examiner.
And this quote right here, this is an absolute goldmine. It comes directly from the principal examiner reports. Candidates referencing cross-topic connections achieve significantly higher marks. So what does this actually mean for a trigonometric modulus function? It means that solving a modulus equation might actually require you to use your knowledge of quadratic equations or coordinate geometry or trigonometric identities. An A-star answer seamlessly weaves these different syllabus areas together. You aren't just solving a trig problem in a vacuum, you're utilizing your entire mathematical toolkit.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section Procedural Framework, from red pen to green check. All of this builds into an examiner-approved, standardized sequence. Think of this as your mathematical blueprint. Step 1. Identify key elements. What is the domain? What are A, B, and C? Step 2. Apply relevant principles. If it's a modulus graph, immediately remember the reflection rule. Step 3. Execute analysis with clear working. Now this is where we heavily rely on the PEL framework: point, evidence, explanation, link. Make your mathematical point, provide the algebraic evidence, explain your steps clearly, and link it right back to the original command word. Step 4. Verify results. Take a value, plug it back in, and check it. Step 5. Present in appropriate format. Are your coordinates labeled properly? Is the curve perfectly sharp where it meets the axis?
Let's look at a real transformation. If you were given just 60 seconds to rewrite the flawed answer you see here on the left, you'd need to extract the data explicitly to build the perfect answer on the right. The flawed answer is completely generic. It entirely ignores the domain limitations set by the question. The presentation is just sloppy. But the perfect answer? It explicitly extracts the data from the prompt. It justifies graphical decisions with coordinates that are clearly written out. It uses proper mathematical notation. Why do these specific changes add marks? Because they completely remove all ambiguity. The examiner doesn't have to guess if you know what you are doing. Your green checkmark answer explicitly proves it to them step by step.
Section 4. Interactive Workshop. Find the flaw.
Okay, I want you to put your examiner hat on. Imagine a student writes this exact sentence on their paper. The graph of y equals the absolute value of 3 sine x goes up to 3 and down to -3, repeating every 360 degrees. I want you to imagine a 60-second timer ticking down. Try to spot the flaw in your head. Okay, did you catch it? The massive flaw here is that a modulus graph never ever goes down to -3. The absolute value brackets mathematically force all negative outputs to become positive. It bounces right off the x-axis. The student completely failed to identify the mathematical limitation of the modulus operator. Spotting these precise, tiny details is exactly the critical analysis skill required to secure those top marks.
Section 5. Examiner Warnings. The top 3 mistakes. We have actually scoured the principal examiner reports specifically for syllabus 0606, and we're going to reveal the top 3 pitfalls that students fall into year after year. First, their answers are just too vague. Simply saying the graph shifts is nowhere near enough. Examiners want highly specific analytical details, like saying a translation of +2 in the y direction. Second, students constantly forget to check format and presentation. Listen, a beautifully calculated maximum point gets literally 0 marks if it's not annotated clearly on your sketch. And third, answers are overly generic. A really great memory hack to ensure you check all these boxes during the stress of an exam is the acronym CAP: Context, Annotation, Precision. Always check your cap before moving on to the next question.
So, the absolutely crucial takeaway here is summarized perfectly by this direct examiner quote. The classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. Think about it. If the question explicitly asks for solutions between 0 and pi radians, and you give your answers in degrees, or you provide solutions that fall way outside that specified domain, you are throwing away easy marks. Contextualizing the mathematics to the exact boundaries given is an absolute necessity.
The final system, guaranteeing top marks.
To completely summarize our masterclass explainer today, you need to follow these 3 golden rules. First, utilize command word decoding. You have to break down the specific requirements and boundaries of the modulus function. Know exactly what your A, B, and C are doing. Second, execute the standardized sequence we discussed by applying the PEL framework: point, evidence, explanation, link. And third, always implement the method mark strategy and manage your clock with the time management matrix. Show clear, explicitly justified working out. Go back to our gymnast metaphor.
Every single line of algebra is a flip, and your final, perfectly contextualized answer is that graceful, wobble-free landing. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainers. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for mathematics and the biggest challenge you're facing right now. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.